Okay, slowly we should get started our afternoon session. Yeah, and the first presentation will be about wireless Part3 as an engineering from Frank Durr. So go ahead.
Thanks a lot. So welcome back after the lunch. So my name is Frank Durr. I'm with the University of Stuttgart. But I will not only give this talk alone. We will have a handover in the middle, and then I will hand over to Simon Egger, who will then present the second part of this talk about wireless area TSN traffic engineering, scheduling algorithms and control plane extensions. So I will start with a brief motivation. Actually, we've already seen the examples that I have in my motivation, so we can maybe quite quickly go over that. Then I will discuss similarities and differences of 5G, 6G TSN bridges and wireline bridges. Also this, we have already seen a few of talks here, but it's very important for our problem statement that we have then afterwards. So the problem would be the robust and efficient end-to-end scheduling with uncertainty. So wireless friendly, wireless aware scheduling end-to-end with these uncertainties that come from the wireless links and a wireless bridge. That's the problem. And then of course our contributions to that. First of all, the control plane extensions enabling the wireless area traffic engineering. And then the second part will then be done by Simon about the wireless area traffic engineering approaches. So more the algorithms, let's say. Okay, let's start with the motivation. Actually, I've chosen exactly the same examples as Marilet did for my motivation here. So we all know, I think by now, that we have two things that we need: mobile communication and dependable communication, yeah? For many of these critical applications that we have in mind. For instance, here is a little example with an HEV or two HEVs, so automated guided vehicles, which are transporting a workpiece together, and they have to move in a synchronized fashion. Otherwise, the workpiece will fall over, or there will be stress on the workpiece will be damaged. That's all bad things that we don't want to be happening here. So they need to move in concert, let's say. And here on the right-hand side, we have an edge cloud environment, which is controlling the movement of these two HEVs here. And in the middle, we have a TSN network. So in the TSN network, of course, needs to enable this dependable communication end-to-end, or as James already said, over the loop, actually. In that case, because we send sensor values from the left to the right, then we do some processing on the right-hand side, and we send back the commands to move the HEVs together. A second example was also already mentioned. That's the exoskeleton, basically the same blueprint. Here we have the exoskeleton on the left-hand side, and on the right-hand side we have the motion control of the exoskeleton now. And also here we have the sensor values going from left to right, and the actuator commands from right to left. And these need to be in time, so it needs to be a real-time communication with bounded delay and bounded latency. Bounded latency and latency variation. And there's many more examples like this here. But what we need for that is certainly this dependable communication. This is here in the middle, the TSN network. On the right-hand side, we see a wired TSN network of wired TSN bridges, but more prominently here, the logical 5G TSN bridge. So this is behaving like a 5G TSN bridge. And this will then also enable the reliable and dependable end-to-end communication together with a wireline network. So we have a wireline network and a wireless network here. The wireless TSN bridge has already been introduced before. So from the outside, it behaves like a TSN bridge. So functionally, it's the same as a wireline TSN bridge. We have the shaping mechanisms here on both ends at the ports. We have a connection to a centralized controller, the CNC, similar to a wireline TSN bridge. But if you look closely inside, then of course you see there's a major difference there. In the insides now we have the wireless links here in this TSN bridge. So where in a wireline TSN bridge, we would have a silicon fabric, which is doing then the switching and the forwarding between the ports. Now we have the wireless link inside of this bridge. This will not change, let's say, the functionality to the outside, but it will change the non-functional properties of that bridge, and it will change that fundamentally. So here's some measurements that we have done with a wireline bridge here on the left-hand side. So this is a wireline TSN bridge, a commercial off-the-shelf bridge, and then a 5G logical TSN bridge here on the right-hand side. And this is the port-to-port delay, as here depicted also on the right-hand side. So from the ingress port to the egress port, yeah, without any shaping, just the packet going through. And on the left-hand side, we see that here we have a delay of about a few microseconds until the packet reaches the other side, the other port. On the right-hand side, we see that for the wireless bridge, there we are in the order of milliseconds already, or tens of milliseconds, few tens of milliseconds. We also see that on the left-hand side, it looks a little bit like a normal distribution. So the probability for very large delays, which are here anyway quite small, decreases exponentially. So they are very unlikely that we have a different value from the mean value, actually. Here on the right-hand side, for the heavy tail distribution, the larger values from the right-hand side of the tail of the distribution, they're not very unlikely. They are less likely maybe than, of course, here the left-hand side, but the right-hand side is not so unlikely as here for the normal distribution. And also the variation is much bigger. So we have here tens of milliseconds variation on the right-hand side for the wireless bridge, and here hundreds of nanoseconds for the wireline bridge. So this is 3 orders of magnitude difference, and I guess as much as the physical layer and everything will improve in 5G networks, 3 orders of magnitude will not easily go away. So I think this is something that we have to deal with it for quite some while, this difference here. Yeah? So the question is, of course, what is now the implication for if you do end-to-end scheduling in our TSN network? So if you want to have bounded delay end-to-end. And Marilet already presented to you what would happen if we apply this QBV scheduling as presented here on the left-hand side. So we have here the QBV model, we have several queues, we have then gate control list, which is a time schedule, which is then saying when which of the queues will be served actually by the bridge at the egress side. And Marilet already presented what happens if we use here end-to-end schedule that is that we are used to be installing maybe in a wireline network. And if you just apply that, then we see there might be these problems that we push some frames to the next cycle, that we have very large delays which are violating the deadlines. This figure here on the right-hand side is taking a little bit of a different angle onto the problem. Here I say, what would happen if you make a robust schedule now that is doing the same thing as we do in wireline networks for a robust schedule? We take the extreme values, the min value of the delay and the max value of the delay from the delay distribution, and we reserve a little bit a larger slot for that. So the frame that we transmit is a little bit smaller than the time slot that we reserve, because the time slot also needs to account for the uncertainty of the distribution. And if you do that, then we can do a little bit of a back of an envelope calculation here. Let's say we have 600 byte frames, we have 100 megabit per second data link rate, and then we can calculate the link utilization from that. So the link is occupied just by the frame transmission time, which is quite short for the, with 100 megabit per second. But we also need to wait the complete time slot, because the frame might arrive a little bit earlier, a little bit later. So we need to have the whole time slot reserved. So the whole time slot reserved means transmission time plus the uncertainty time. And if we do the calculation then for the wireline bridge, we still have a 94% link utilization, which is still quite okay. But if we take into account the uncertainty that we would have now with a wireless TSN bridge, then the uncertainty interval is much larger, and then we would drop far below 1% link utilization. And this is not acceptable, of course. So if you would make a robust schedule with the conventional approaches, then the efficiency would go down drastically. That's the message here. Okay, so what are the contributions to solve this problem? There are several contributions. First of all, we have extended here this control plane interface by making the CNC aware of the wireless distribution. So this is the idea here. We have defined a Yang model, which I present in a few minutes in a little bit more detail. And with this Yang model, we can transfer the information about this uncertainty of the port-to-port delay to the CNC, and then we can run there some intelligent algorithms which take into account the uncertainty, which can then calculate a robust and hopefully efficient schedule knowing the uncertainty. So that's one extension. Second extension, Marilet has already presented in very detail. So everybody should know now that this packet delay correction is a very useful tool for also maybe using and removing the uncertainty. And then using the wireline TSN scheduling algorithms maybe. So on the left-hand side, we have a lot of uncertainty maybe in this wireless bridge, but with PDC, we could remove this uncertainty completely if we like, and then use on the right-hand side in the wired TSN bridges a conventional wireline scheduling algorithm. And this is, of course, very nice. Then we can build on all the work about wireline scheduling. But we have a little bit more than that. We also have wireless-friendly end-to-end scheduling algorithms that could then calculate a reliable, a dependable end-to-end schedule, a robust end-to-end schedule using these delay distributions also without a delay correction, but also with the delay correction. So we can combine both approaches at the end of the day. The delay correction to remove maybe a little bit of the uncertainty, and then the wireless-friendly scheduling to guarantee that we have a robust schedule end-to-end and still have the efficiency that we need much better than we had with these conventional approaches. Okay, so let's go a little bit into the contributions. So the first contributions I will briefly present. So that's the control plane extensions for delay uncertainties. So this is what we mentioned already as this contributions towards the standard 802.1 QEE. So this is, there's the idea is that we define new Yang models, so extended Yang models to what's existing already in the standard. So in the standard so far we have Yang models that can define a port-to-port delay for a bridge. But it's targeting wireline bridges. And that means what these Yang models can only do so far is they report a min value and a max value. So a very conservative bound for this delay distribution, which is maybe okay for the wireline distribution because anyway, this delay variation is very small. Yeah? But this means that we have to stick with 100% reliability for scheduling because we don't know anything about the delay distribution inside. So if you want to have 99% reliability only to cut off the long tail, for instance, that's not possible with this model here, the existing model. So what we did, we extended that to a fine-grained delay description, and then we basically can transmit a whole histogram in different granularity, if you like, to the CNC. And then the CNC sees this histogram as we see it here on the right-hand side. So that's one feature of the model. Another feature of the model is that we also have the possibility to define a lifetime for this distribution. So we have a distribution that might change over time. If you look at a wireline bridge, we have a silicon switching fabric. There, the port-to-port delay does not really change. It's by design, as the forwarding mechanisms work, it's almost always the same, so the worst-case bounds will not change. But in a wireless network, these distributions might change over time. And we can update them now with our new model because we define a lifetime for these delay distributions. And this also enables us then to implement something like a make-before-break scheduling approach. Actually, calculating an end-to-end schedule with QBV takes some time. It's an NP-hard problem. It's a very complex problem, actually. So we cannot calculate schedules below 1 second. And that would be already very fast, actually. An end-to-end schedule takes, for calculation, typically maybe longer than seconds. But with this approach here, we could know that maybe the delay distribution changes over time. And with the delay predictions that Sami presented, we can have the prediction of the delay distribution already in advance and then calculate a new schedule before the old schedule will break. And then we have the new schedule available when the old schedule becomes outdated. And then we can have a seamless adaptation in our network of the end-to-end schedules. So that would be the second feature of this extended model. And for the next part, then I would hand over to Simon.
Thanks. Good. Thanks, Frank. So for the next part, I think I mainly want to focus on the architectural integration as well as the algorithm integration of what we can achieve when the 6G system, for instance, with PDC and the end-to-end wireless-friendly scheduling works together. So the individual components, to highlight them here, I would say, of course, first off, we had a nice presentation of Sami that focuses, first of all, on the prediction within the 6G system. And of course, we rely on that in the first place. So in here, for instance, we can have delay monitoring. What are the individual components that cause this 6G delay in the first place? And I would even argue that it's important to distinguish here what's actually occurring here. So in this case, we have a separation between queuing delay variation, and that is simply due to the, that's basically a synchronization issue between the end-to-end TSN scheduler and the 6G transmission offsets that we have. And I would argue that we can eliminate those entirely if we have a sufficient synchronization between both systems, right? But at the same time, we also have this stochastic delays that we cannot fully control from the end-to-end system, and we also don't want to control that from the end-to-end controller. So here we in general also have to distinguish that within the 6G system, we can adapt at much faster rates to such small-scale fading effects, for instance, while at the end-to-end control that we have, for instance, at TSN, those adaptation processes typically take much longer. As Frank mentioned before, it's often considered as an NP hard optimization problem, and even if we design nice heuristics for them, you still have to deploy those configurations via netconf, and all of that together can take up significant time. So I would also say we are here at a range of 500 milliseconds and above, whereas with the 6G system, we are certainly at much faster rates. But having said so, we do require these delay characteristics, which are then sort of transformed into these histograms, which can also be used by the end-to-end scheduler later on. So let's focus on that part next. So here in Deterministic 6G, we generally designed two possible approaches to do that, and they work on their own, but also they work together. And the first one here would be actually packet delay correction, as Meredith presented earlier as well. And there we internally have, within the 6G system, a delay or a delay variation compensation, right? So we try to make the 6G system appear more deterministic by delaying or jittering frames at the egress side of the 6G system. At the same time, we might not be able to dejitter them entirely, depending on the technical capabilities, or we can also try to compensate that from the end-to-end design that we have within the TSN domain. And that is what we call wireless-friendly scheduling. So we try to make the end-to-end scheduler, the TSN scheduler, more robust against such delay variations that can now be in the range of milliseconds rather than microseconds. And at the same time, one thing that I also want to particularly mention here with the wireless-friendly scheduling approach is that we can also enable certain options for graceful degradation. And that is sort of what Oliver mentioned earlier with regards to the level of operation that the application might be interested in. So if we have a certain information now at the end-to-end controller as well, we can have full control over the histograms and try to, of course, internally adapt as much as possible without notifying the application. But if we are at one point unable to do so, then of course we would notify the application to maybe decrease the level of operation that we can now achieve. And the one part that I want to highlight here as well is sort of the contract that we have between TSN and 5G. So our general approach for the wireless-friendly scheduling design is to take those histograms and, depending on the stream reliability requirement, which in this case is 90%, we allocate a certain 5G packet delay budget. So in the nice case of 90%, we can even see that we don't need to consider the long tail, but it's sufficient to only capture the mass of the histogram. So with 4 to 8 milliseconds, more or less, we can capture this 90% reliability sufficiently, and thereby we essentially tell the 5G system that is what we require from you within the next time epoch. So let's say maybe over the next 5 minutes. So afterwards, the 5G system internally has to uphold this contract. At the same time, from the TSN perspective, we can now work with that. So we don't need to consider the entire histogram from 4 to 14 milliseconds, but we can take this 5G packet delay budget and use that to configure our QBV gate control list and even our per stream filtering and policing. And thereby, essentially, what we do is that we extend the 5G guarantees end to end from listener to talker. And so what we basically saw at this point is that with wireless-friendly scheduling, we can take arbitrary histogram information, select a certain slice out of this histogram, and compute an end-to-end schedule. And then it's quite intuitive that that automatically works together with packet delay correction. So what you can argue is that packet delay correction essentially modifies or augments this histogram by saying we shift a certain mass of the histogram from the left to the right. So that can still be used as an input for our wireless-friendly scheduling design. And I'm now skipping this slide because Meredith mentioned that earlier, of course. But what I also want to iterate now upon is also a quick simulation that we did for our wireless-friendly scheduling. And also here, we simply took our our 6G DETCOM simulator, and we also distinguish between wireless and wired streams. And the particular interest here, of course, is that with wireless streams, we now have a reliability requirement that we vary between 50 to up to 99.99% reliability requirement. And the other part that is worth highlighting here is, of course, that the wired streams have much more stringent latency and jitter requirements compared to the wireless streams. But at the same time, if you look here, the jitter requirement that we now have with wireless streams, those are no longer in the range of milliseconds of what we have typically with the histograms, but we are now in the range of hundreds of microseconds, or we could even go below that. And here with this plot, we compared FIPS, which is what we call our wireless-friendly scheduling, against related work that already exists and tries, for instance, to take the median delay of such a histogram or the maximum delay even of the histogram, but they don't account necessarily for the packet delay variation. And with FIPS, what we see is we stay, of course, below the intended end-to-end latency, and we achieve the 99.99% reliability requirement of this high criticality stream. But essentially for the non-robust approaches, we see something very similar to what we had earlier with packet delay correction. So there are these uncertain queuing orderings, these uncertain transmission orderings, and they essentially can cause a queuing backlog to be built up and essentially even push frames beyond the hypercycle and certainly beyond their deadline, what we see here on the left-hand side. At the same time, and that is something we discussed yesterday in the summer school mainly, we also need to account for scalability in a certain respect. So with the conventional approaches, one typically uses an exclusive time slot reservation, where we essentially allocate a certain 5G packet delay budget for one stream and one stream only. And dejittering that can be very expensive, what we see here with the yellow bars, which represents what this exclusive time slot reservation does. So we can, in general, only schedule very few streams by doing so. And in contrast, what we do with our wireless-friendly scheduling design as well is that we try to have a dynamic frame batching. So if multiple wireless transmissions occur at the same time, we essentially queue them up, dejitter them, and open the gate once to send out a certain stream batch at the same time. And thereby we can drastically increase the scalability or the number of wireless streams that we can schedule. So to summarize, the key challenges, I would say, for the integration are certainly that we have just an entirely different characteristic profile with our 5G setup. So we are no longer near deterministic as we had with wired TSN, but we are now stochastic and need to account for this delay variation that we have. At the same time, there are certainly integrational aspects like making TSN and 5G isochronous simply to eliminate this additional queuing delay that we had earlier, what also Sami mentioned. And the proposed solutions are sort of complementary in that we have control plane extensions to expose those 5G histograms to the end-to-end control. We have wireless-friendly scheduling that comes from the TSN side and tries to work with these delay variations. And at the same time, we can of course also come from the 6G side and try to make the 6G system appear more deterministic. And with that, we're also at the end of our presentation, and thereby I'm also happy to answer any open questions.
It's a very clear presentation. Online?
There's one question over there.
Thank you for the good presentation. In the simulation there, you combined the delay compensation with the other method, but did you also simulate without delay compensation, and how good the results were in those?
So here, actually, in both the simulations, we do not include packet delay correction, but only wireless-friendly TSN scheduling.
Okay.
But we also do have a work that I mentioned here, That's a magazine paper where we also try to combine both aspects to have a look at how they complement each other.
Okay, thanks.
Anyone else?
Any questions online? Good.
Thank you.
Thank you so much to the presenters.
Okay, thank you so much, Frank and Simon. And now I guess we will have an interesting journey to the security domain. So Edgardo and Unia. So please, floor is yours.
This is it. Okay. Nice to be here. So I will start the presentation on security monitoring for 6G. And my name is Edgardo Montes de Oca, and also Unia and Nguyen will also present what he did in the Deterministic project. So first I'll briefly present our company. Montimage is an SME that was created in 2004 and located in Paris. So we bring together a group of cybersecurity and cyber defense experts and researchers. And we are strongly involved with academia and other companies to work on the research, different research topics, notably on security, cybersecurity and 6G. And we developed an open source solution that we call MMT, which is a monitoring framework for analyzing the performance and security of the networks, different type of networks, including IoT, 5G, and we also developed a pen testing tool that we call 5G Replay, which is like TCP replay, but allows generating 5G traffic and modifying it to be able to test the robustness of different network elements. And we also worked on, and notably on deterministic 6G, on the use of P4 and machine learning-based in-band network telemetry. And we also built instant, what we call an instant 5G network, but it's used mostly for testing, testing our tools. And then we also provide cybersecurity, cyber threat intelligence services, and security audits for companies. And we participate in several collaborative research projects, notably concerning 6G. There's a deterministic 6G, of course, and network. And also in other projects where we provide tools for cybersecurity, like AI for security, AI for cyber. So first I will give a brief introduction of what we see as what is security by design. And then Unia will present his work on the monitoring of PTP packets to detect attacks, time delay attacks. So what is security by design is making security intrinsic and embedded in an embedded property in the 6G architecture from all aspects. So one of the main pillars of this cybersecurity for 6G is the AI native and adaptive security, because today most of the traffic is encrypted. So to be able to analyze and detect anomalies, we need to use machine learning techniques to be able to differentiate anomalies from normal traffic. So this allows continuous real-time threat detection, prediction, and automated response, which combined with cyber threat intelligence allows to prevent ongoing attacks in the network. And then another aspect that's very important is the zero-touch security management, because the complexity of of the 6G, 5G and 6G is so big that not all tasks can be done by humans. So we need a self-healing network that automatically reconfigures and isolates attacks, like using techniques like moving target defense or slicing to be able to isolate the attacks. And this also implies defining the trade-off, because we cannot have 100% security, so we need to be able to determine where when there's real risks, when there's real threats, and define the security level that is needed for the applications. And then one other aspect that's important for the zero-touch security is be able to define the security from a user's perspective or the operator's perspective, and that this be translated so that it can be assessed and verified in the network using monitoring techniques. So other aspects also need to be considered in security by design, like physical layer security, by, for instance, using the properties of wireless channels to generate secure keys, or detect eavesdropping, or avoid eavesdropping. And also another aspect is this, what is called distributed trust and ledger, the use of ledger technology to decentralize the trust management, and make sure that even in situations where there could be attacks, that all is done to make sure that the management is protected and trustworthy. And then when you have confidential computing, which includes trusted execution environments, to make sure that when you execute applications or services, network services, they're not vulnerable to attacks. And then you have also the zero trust architecture, which implies a continuous authentication authorization of all the devices. And this also implies using post-quantum cryptology. So the high-level architecture of an end-to-end security monitoring and management framework implies that we need to be able to deploy probes in different points on the different domains in the network, which includes the TSN domain, but also the core and the RAN, etc., and the IoT networks. And in each of these domains, we need to be able to analyze what's going on to be able to detect anomalies. And then this also has to be coordinated at the end-to-end level, so that the security can be coordinated between the different domains, and the security function be deployed when necessary or changed when necessary to be able to protect the systems. And here I can give an example of what can be done to obtain a closed-loop zero-touch security management. So we need to define the intents or the security SLAs, service level agreements, and this allows to define, for instance, time-sensitive KPIs that need to be respected, like maximum delay tolerance, and also define the trade-offs, like I said before, and also define the interdomain security management that is needed. And then this can be translated and used to the zero-touch network service management to automate the detection and the management of the reactions. And this requires, in the context of time-sensitive networking, requires precision monitoring, timely response, and also with the intent of improving the time-sensitive service continuity. So here in the diagram, you define the policies or the SLAs, and this has to be deployed in the security analytics engine and the security orchestrator. And then when the security analytic engine identifies an attack, which was detected by the security agent, which is a probe that is distributed in in the domain and infrastructure. And this probe will inform the security analytics, which will analyze this and determine if it's an attack, and then inform the orchestrator so it can take a reaction. So security monitoring, first of all, we need AI and explainable AI, because security monitoring can be used to capture the data needed to train the models, but also is needed to be able to detect the anomalies, and these have to be explainable to be able to react. And then in that way, the definition of security policies, intents, and SSLAs, like I said before. And then we need to constantly verify the security posture of all the assets, and also consider the slices, and also incorporate the information coming from the cyber threat intelligence, and to detect the anomalies and react using self-healing techniques. And finally, what we need is end-to-end monitoring of all the domains to be able to deal with the time-sensitive applications. And this will be explained by, given a concrete example by Unya. So he will talk about PTP monitoring, and I'll give you the hand.
Thank you, Edgardo.
Ça marche?
Hello, can you hear? Yes. Thank you, Edgardo. So, Hung Yang Nguyen, a research engineer from Multimatter. So now I will show you a concrete example how we can apply the security framework proposed in the project to secure PTP. So first of all, I assume that you know PTP protocol, but basically it is used to synchronize the timestamp between two machines. We have a client and server. The objective is to have the same timestamp from client to server by exchange of 4 messages. Sometimes we need only 3 messages to get the time synchronization. And in general, client does not connect directly to server via a sampler cable, but it can go through different elements in the network. The element called transparent clock, so that when packet go through the element need to modify the correction field inside the PTP packet to add the resident time of the packet, so that PTP at the client can calculate correctly. So now, why PTP? Why do you need to secure PTP? Because we know that PTP is a basic element in the TSN or .NET network to provide the same timestamp between all the elements in the network. And there are one appendage in the PTP protocol to prevent hacker or malicious person to do the attack in the PTP protocol. However, this appendage cannot prevent attacker from a time delay attack. So time delay attack, it means that attacker do not modify the PTP packet, but it capture packet and hold for a certain times and then forward the packet. We cannot neither protect, prevent the attacker from this attack, but we can detect whenever the attack happens in the network by using monitoring, and then we can raise an alert to the network administrator, for example, to do the mitigation. So now I will go in the detail our framework, how we can monitor the PTP packet, and then how we can detect and localize the time delay attack. So first of all, we need to know what is the time delay attack. We assume that someone, an insider, for example, it can capture it can intercept the communication between the client and server. And we can see that if the attacker can introduce a delay of delta in the sync packet, then he can declare the client clock by a half of delta. And if the attacker can introduce an additional delta in the delay request packet, then he can increase the client clock by a half of delta. However, if the attacker introduces a delay in both sync and delay message, there are no effect in the client clock. So he need to introduce one way the delay of the PTP packet. And we see that we cannot prevent this kind of attack, but we can detect this kind of attack by relying on three signatures. First of all, the attack must continue because once the attacker stops the attack, then the client clock will be correctly synchronized in the next cycle of synchronization. And the server, we see that does not influence by this kind of attack. And the last one, we can see that the attack outside of a transparent clock does not influence the transparent clock. Even we can assume that an attacker can compromise the transparent clock in order to modify the packet or to capture the packet or do something to do the attack. So here is how we can detect. We can detect by monitor the arrival time of the PTP packet, because if attacker introduce a delay, then the packet should arrive after a certain delay. And we can see that if, for example, if the requirement of the time synchronization is a T, for example, I need to have a, I don't know, 200 millisecond of accuracy, then we can raise an alert if the delta, if you can see the delay of the packet is more than WT plus a sigma. Here we add a sigma is as a sensitive of the detection. So here is how we can apply this kind of monitoring, because here we have a client and server communicate via a network. So first of all, you need to calibrate the PTP protocol in order to have the same timestamp. And then we need to learn how much accuracy the network can support. For example, if we require that the accuracy is 1 millisecond, however, the network can support only, can give only 10 milliseconds of accuracy, then we don't need to monitor the attack because it always it does not meet the requirement. And from that, after that we can monitor the arrival time of the PTP packet, and then we raise an alert if we can see the equation is not satisfied. So how we can monitor the PTP packet? Here is an example of the test bed. Later we see a real physical test bed, but here we have a emulator based on Mininet test bed, so that if you want, you can reproduce the test on a single machine by using the emulator. So here we have a network consist of a server running Linux PTP, that is an implement of PTP protocol in Linux, and we have a client. It runs on a separated machine. We use a Raspberry Pi because we don't want client to modify the timestamp in the system. so that we have two machines separated, two separated machines. And then client and server, we connect via a lot of transparent clock using P4 programmer. So here, each time the packet go through a node in the network, we add some information inside the packet. That's why we call in-band telemetry. It means that we monitor the packet and we do not generate the result in another packet, but inside the packet we are monitoring. So that's why each time the packet will go through bigger and bigger. And at the last element of the network, we need to extract the monitor information inside the packet and send it to the data collector. And we reset the packet to the original format so that the client does not see any modification in the packet. So here is the information we put inside the PTP packet. First is the ID of the element in the network, and timestamp when the packet arrive in the element, when it's go out the element, and the correction field of the PTP message before arrival at the element in the network. And here we can see graphically representation of the packet in the Y-SAC. So here we have a PTP packet, and we introduce three custom PTP TNV tip length values to contain the information, the monitoring information. So this is we see later a monitoring graphical interface to see the variation of the interval arrival interval times of the PTP packet in the first one, and this variation with respect to the variation of the master, we can see that the synchronization packet send almost 1 second, but the delay request can vary from 0 to 2 seconds because the standard requires that. And if we detect some attack, we can see here, for example, the attack, the time delay attack is located between the switch 7 and the master, switch 7, 8, 9, 10, and the master. And the last one we see to show the arrival time of the packet at each element in the network. Here we have no before here. Here we have a test bed in an emulated environment, but here we have a real physical test bed. Basically, we have a PTP master. It connects to an UE end user equipment. The end user equipment we connect to the Z-Node B. Z-Node B we connect to the 5G core inside the Dell laptop. Inside that we have a UPF. UPF we send the packet to the PTP slaver. And before the packet go to slaver, we send the monitoring status to INT collector. So I will show the demo in the after this. Okay. And for conclusion, Edgardo, do you want to?
No, go ahead.
Okay. So we introduce a kind of monitoring using in-band network telemetry using a P4 programmable data plane language to monitor the PTP packet. We publish our solution as open source. And for the future work, because for now we use P4 to monitor, but in the future we want to integrate also the detection mechanism inside the network element. we also need to explore different time delay attack model, because for now we interpreted only the constant time delay attack. It means that the attacker introduce a constant delay in the packet, but he can introduce a different delay in the packet or a randomly delay in the packet. We need to study the mitigation strategy. If we detect, then how we can react, how we can mitigate. And for the reference, here is the paper we published. This works. Okay.
Thank you.
Okay, thank you.
Any questions?
Thank you very much for the very informative presentation on securities. I'm very interested in the concept of physical layer security. So, of course, we can address the security at the higher layer. But can we use any particular modulation or the waveform as a physical layer to ensure the security? What do you think?
Yeah, there's a lot of techniques that are being used for the physical layer security. To avoid eavesdropping or things like that, but and assuring the security of the communication using encrypted tokens or things like that. But I'm not very much aware of all the techniques now.
Okay. Well, because in the part we have the CDMAs, so the code division multiplexing access. So I'm not sure whether it can fit in the context of physical layer security. Anyways.
What I didn't understand the question.
So in the past, in the mobile communication, we have the CDMA technology. So it's quite secure at the physical layer.
Not completely. No, I don't think so. No, because you can have a compromised or fake stations, E-node, G-nodes, things like that. So you have to be able to avoid that. And also you can have compromised mobile devices, no?
Okay, yeah, thank you.
Okay, so thanks for a very interesting presentation on security. So as far as I understand, your approach is to build probes to monitor whatever kind of attacks, and then you mitigate. And in this specific example, that probes is built using P4, right? And
Yes.
if that is the case, then where you put that probes exactly in the wireless stack, or I'm sorry, in the P2P stack. That's the first part. And the second part is regarding to your future work. Then suppose you detect some kind of attack. What would you do to mitigate that? So thank you.
Well, one technique is to have not only one slice providing the synchronization, but have another one that replaces it. Yeah. I don't know if you have.
Yeah. For the first question, maybe we go back to the
Yeah, would be
this.
nice.
So here we put P4 in the we call UEDSTT. So when the PTP packet go to that, we modify the PTP packet to add the monitoring information as I saw in the graphical interface of the WiSock. And this packet will go through the 5G network. When it goes through the 5G network, we do not modify anything inside that, because the 5G network is we can consider as a logical transparent clock. Okay. And when it go out to the UPF, here we have a component, another component to add another information inside the PTP packet. So that is how we use P4 to and the position of modification inside the packet. And for the second question, how we can mitigate, I think the first, already we know where the attack happened. So maybe the first solution is isolated this segment of the network to avoid further impact, and to redirect the packet to use another path to the client. And for the other, I don't know, I need to investigate more about that.
Yeah, thank you for the insightful information. I will surely visit your booth. Okay, thank you.
Yeah, it's right here. Yeah.
Yeah, one practical question. So, I mean, achieving this accurate time synchronization across the 5G system is quite, I will say, sensitive, because you need to get these hardware timestamps to do the egress and the egress. Have you seen any major impact when having the TCO and TC1? I mean, I know that they are before the DSTT or after the DSTT and before the NeoTT, but then have you seen impact in the overall time synchronization? Because when the packet arrives, first it comes to the TCO, it might have some delay, then it goes to the NeoTT, timestamp, blah, blah, blah. Have you seen any sort of impact in the overall time synchronization accuracy?
Impact in the time synchronization, maybe I do not have more information to respond about this question. However, I want to clarify that even if the time synchronization in using this testbed is less accuracy, but it is not what we are interested in. What we are interested in is if the attacker can make this accuracy even lower. If it is the case, then whenever we can detect or that or not. I don't know if you see the point.
I can just say that the moment you modify the delay by holding the packet, you ruin the whole simulation, the whole time synchronization, sorry. Yeah.
That was my question, if they have seen any kind of impact by this.
Yeah, but regardless, it's totally destroyed the track of the time synchronization.
Okay, so thank you, Edgardo and Hunia.
Thank you.
And in the beginning, we have mentioned. In the beginning, we have mentioned that the project aims to investigate the architectural aspects of 6G dependable communication. And at the end, to some extent as a conclusion, we will give a concise overview of the required architecture components for realizing this 6G dependable communication and compute by Joachim Sachs. So, Joachim.
So, thank you. Does it work with the audio? I think so. Okay, welcome. So I will, it's a little bit of a summary to some extent. It's basically puts on what we have heard during the day in the context of an architecture. And we say it's a 6G architecture view on dependable communication. And starting from what is the objective that we have? So we want to enable critical applications, and what we mean, which means applications which we provide from the network with a connectivity service. And what we mean with a critical application is that we have an application which has a certain traffic profile. And for this, the traffic that enters the network, we want to be able to provide critical or certain performance level where we know that they are critical, which means they are needed for making the operation of the application work. Which means if we fail in providing this minimum performance, which could be a maximum latency or it could be a minimum data rate, if we fail for providing these performance level to the applications, then this implies that there's some failure of the operations of this application. And then there's a certain severity of that, which means this failure can lead to well, depending on the applications, it has different applications. It can be in a, we heard it from the use case on industrial automation. It can lead to an emergency stop of an automation system. It can be a safety risk. It can be some other kind of loss that is incurred by not having the applications working properly. And that means that in the context of what does it mean for if we define a service level agreement where we define these minimum key performance indicators that need to be achieved, it would be basically the severity would say, what is the availability that I need? What level of guarantee do I need to have in order to get my applications running with these performance bounds? Then, of course, such an SLA can be also further described that it's maybe only valid in a certain specific area or at a specific time. But this is basically the kind of contract that the application wants to make with the network for obtaining a connectivity service. And if you want to make this connectivity service dependable, it means that the application can simply rely on that the network provides the performance and the availability for the applications to run at a satisfactory level. And that is what has been defined before in this service level agreement. So that is what we are after. And the question is now, how do we support this from the architect, from the network? And I mean, we have heard different components that play a role here. How do they fit into such a network architecture? We've seen this definition also before in the talk of James. So I mean, we broke this dependable network ambition down into what does it mean in technical terms. So we come to this definition that a dependable network can quantitatively ascertain that it will deliver the required service performance for the network services according to performance levels that were agreed upon. And there are several parts here that have a technical implication on how to achieve that I will address during this talk. And this will be something about, I don't have a pointer, so about being able to deliver a certain service performance, being able to quantitatively ascertain this performance, but also having the mechanisms to agree on those terms. Starting on when we talk about an architecture, I mean, one way to think of an architecture is such a layered view here. We see in the middle the 6G system, which means we have the 6G system contains, I mean, you see there in the middle layer, access, mobility, and network functions. This is the functionality of the network. It is realized based often on a cloud infrastructure, which means some of these functions are realized on a distributed cloud platform that is used for the network. We have transport network in between for interconnection, the different nodes in the network. And then we have a management and orchestration layer on top in order to configure and operate the network. Now, our applications typically, they run at end nodes, which are then connected via this 6G system. There can be additional networks in between. For example, we can have a data network that connects this end node to the 6G system. And also on the device side, it's not always so that the user equipment of the 6G network, the 6G mobile device is the device which hosts the application. It can be a gateway, and then there can be some kind of local network that is actually in the end hosting the application. And this application has to provide to the network its requirements, like for what I said before with the service level agreement, or it can be, if it's maybe a private network, it will be some specification of service level objectives that the network need to fulfill. And it's not always so that the application directly interacts with the network in order to provide this information. Often there's some kind of application middleware involved that is then in charge for configuring the connectivity for these different applications. So for example, if you go into the industrial systems, then often there are engineering tools, or in OPC UA, there's a connectivity manager in which you basically configure for different applications what their requirements are, which means we have maybe this middle layer in this configuration process. And then if we have these end-to-end applications, you typically have some kind of networking technology that provides you with a dependable connectivity end-to-end. And that is then in the LAN segment, it's typically this time-sensitive networking as extensions to Ethernet as the technology that is considered. Or if we go more into IP networks, which allow us to have a slightly larger scale of the network, then IETF has defined the DETnet as the kind of TSN equivalent for the IP network. And this is then how you would connect your applications end to end, and we have this 6G network then in between. Now, not all of these applications, if I start here, are directly located at an end node that is connected to the 6G network, but there's an increasing adoption of using cloud technologies for operating your applications. And that means that the applications that we see here on the network side is actually implemented as a virtual function in a cloud environment. And if we think of edge computing, then this cloud environment is basically integrated with the network as a capability, which means that that also our management and orchestration stretches into this edge compute domain. Now going back to these different parts of the technical features that are in the definition of dependable connectivity or dependable network, I said, well, the first thing that we need is we must be able to deliver the required service performance. And when we think of time-critical communication or time-critical applications, this means in particular that we can provide guarantees on the latency performance that we can provide to the applications. For this, there has been quite some work on time-critical communication, which uses functionality that was specified under this ultra-reliable low latency communication features. And that means that we are not having, like in mobile broadband networks, a characteristic where we have very good average latency performance, but then we have a tail that we actually cannot really control, but that we introduce features into the network where we can basically control the bound of the latency and provide this with a certain guarantee and thereby giving an upper bound. Now, the details of the technology for this is something that we have not really addressed in our Deterministic 6G project. This has been a lot of research has been ongoing in this in other projects and in standardizations towards 5G. But we simply assume that such functionality is available and that we can make use of it in our creation of a dependable connectivity service. So here are some references or where on these time-critical communication is being worked on, and this is just a short list. There are many more papers which describe this at large. But so this is something that we assume that we have the performance capability in the network. Then how can we make this or turn this into a dependable connectivity service? The next thing comes here that we must be able to quantitatively ascertain that we can provide a certain performance to an application. And that means that we must be able to simply know what is the performance that I'm actually delivering, which means we need observability, and with that also we link this to predictability that we have heard before and that I will talk about a bit more. So if we think of delay, then if we want to know the delay that we are delivering from the network, then we must have some observability means of saying what is it that the delays we actually occur in the network, which means we have here, if we look at the green lines there, we want to have a feeling of what is the delay that a packet has as it goes through the network. And for the delay, when we think of observability, it means we need basically two observation points that we to determine the delay. That is the ingress point and the egress point, and between those we have the delay. Now, in order to define a delay, and we have two observation points, we must make sure that these two observation points describe the time when a packet arrives at these places with regard to a common reference time. Otherwise, you cannot determine the delay. And there are some mechanisms in the network for 5G, and it will be also for 6G, on having time references that are shared in the network. For example, the radio network that we see here on the bottom, that is always time synchronized because our operations of the physical layer of the radio network simply uses a synchronized operation mode. But what we have also standardized in 5G is that we can, for the purpose of time distribution over the network that we've partly seen in the talk before for the security analysis, there's a method standardized how you can transport time over the 5G network. And in order to do so, there are mechanisms specified to synchronize now the user plane nodes, which is the device, the UE, the base station, the G-node B, and the gateway function, the UPF, to a common reference time. And with that, we can basically make a probe on the packet as it enters the system and look at it at the egress point and determine the latency or the delay that the packet has spent in the system. Now, the performance of latency is strongly dominated by the performance in the radio network, which means we get a very good point also if we observe the radio network separately, and the monitoring of the transport network between G-node B and UPF is an easier task. Right. In order to do this, then we see here in architecture we have the applications left and right. We have the network, in green, the radio access network, the core network on the right-hand side in blue. And now, as we operate the network, we want to get these measurements of the delay, which means we basically have a data collection of measurement points which tell us about the performance that we deliver to the application in delay. And this is something that we can store and analyze. And by that, after we have made this promise on a certain, for example, there's an SLA about I must maintain 10 or achieve 10 milliseconds with a probability of 99.99% or so, I can look into my historic data and see, did I manage to fulfill this SLA? But once I have this information collected, I can also use it as basis for prediction, which means I put it into my machine learning model, train my model, and afterwards can use the inference of predicting what is it that I can, what promise on latency can I give with which reliability based on these trained models. Right. We have also seen once I do this observability, and that was in the talk before, then I can of course also use it for analysis in other dimensions, like for example this security assessment by looking into anomalies in the distributions of PTP messages, what was just presented before. So I mean, this observability is a tool that can serve multiple purposes. But so now I have talked about this, the very important need for having observability in the systems for simply getting the insights and the awareness of the network of its own capabilities and operation performance. A next step then is to think about this in connecting this into programmability and adaptability. And what this means from an architecture perspective is that I have my access, mobility, and network application functions. They are those which mostly basically influence the performance of the network or have the functional realizations of the network. And now I want to be able to get from my applications, well, first when I want to establish this service level agreement or service specifications that we heard by Oliver before, I need some means to have an interface into the network where I can describe what my needs are. And this is something which is in this layered architecture coming via this exposure layer, which is basically a way for having an API-based interaction model between external functions with the network, for example, for requesting a specific service level objective. But I can also use this information, this API in the other way by using the network where I have my certain insights into the network, for example, from the observations and predictions, and use this towards the TSN layer or my applications directly, for example, for enabling this adaptations that Oliver presented, where an applications, if you can basically estimate, it's very unlikely that I can maintain my current performance level for a time, and you can give an indications, then the applications could react by changing this level of operation and going to this degraded mode. Now, for TSN, we have heard about this before in the talks. I guess it was actually 2 talks in which we had this partly, which means we have now our TSN or DetNet controller, which tries to control the system end-to-end in a way by being aware of what the different components in the in the network contribute in uncertainty and latency latency characteristic, and configuring it accordingly. And we have here the TSN bridges, the wired bridges that are deployed. Then we have the 6G network here. And we also have now that we have if we have cloudified applications, that we have uncertainty which comes from the computation time, that we don't have a dedicated computing platform for our applications, but it's a shared resource in the compute domain. And we have actually provided from the network, I think I have it on the next slide, we have provided measurement data sets for all these domains. We have different 5G networks that we have used for analysis with different frequency band and different configurations and different trial systems that were used. We have measured these wired bridges that Frank presented also before. We have also done measurements in the of an edge compute environment, and by that characterized this. And these are data sets that are also made available so that we can use them, for example, in these open source extensions that we have made to this TSN simulator, because we want to have the community also using this and simply making sure that in future there will be good wireless TSN also solutions, because everybody works on it and makes improvements, and this will become successful. Now, when we think about this cloud domain, we also have, as I said, we have now a situation that if we have a cloudified application, then our applications is there in this right-hand side cloud domain. And there's, of course, a certain computing time for running your, if it's a controller or whatever, which has, as I said, in a shared compute environment, has a certain uncertainty associated to it as well. But it's not only the compute itself, but it's also that this, this function needs to be connected in the end to a network interface, which connects it to the rest of the network. And this is in the cloud infrastructure realized by some virtual network within the compute platform. And in order to be aware of these characteristics, we have proposed to have an extensions to the control plane of the cloud environment, where we have the awareness about the characteristics of the compute uncertainties and the uncertainties of this virtual network in the cloud domain to access the network interface card, and that this can be used then in the interactions with the TSN domain also for making appropriate configurations for your end-to-end operation. And this is something that is also reported. I mean, we've probably also seen this, that I have listed the references where we have much more information about the different parts that are mentioned here. Now, for this end-to-end traffic management, I think it was almost covered before in the presentation as well. So we have now this controller which takes all these different domains into considerations with their characteristics, and we have looked into multi-domain TSN traffic management. We have started or initiated the upcoming standardization towards this wireless-friendly TSN extensions, and we have looked into how we can improve from the 6G network the characteristics towards this end-to-end management, for example, with this packet delay compensation, where we can get rid of some of the uncertainties in the delay performance. What we have also looked into is the interactions. Once we have collected the information about our network, and we have this insight, we have something like, we say, well, this is information that we could say is stored in some network digital twin, where we have basically awareness about the capabilities and the characteristics of the network that we are operating. Something similar exists also in the application domain. I mean, if we have a cyber-physical system of something more complex, then typically even this cyber-physical system has a digital twin, or at least a platform where the tasks and the interactions for the different enterprise assets are planned and configured. And we have investigated, can we improve these interactions by sharing informations between these domains? And this could be done as is shown here. So we see on the right-hand side that we have a network which has certain, well, it has different elements. And out of the operations of the network, for example, with this observability and prediction, we can characterize how the network behaves and what capability it has. And this is something that we can abstract and describe in a way that is useful for an application and share it with an application. And this could be, for example, that we can, if we take now a factory environment, we could say, we could have an overview of, for a certain deployment, what is the capacity that is available in different parts of the area that is covered, or what are the latency guarantees that you can give at different locations, or what is, well, how many applications of a specific characteristic would you be able to serve with a high reliability in different places. This is information that could be used, for example, in the application domain for saying, well, should I send now 10 mobile robots at the same time into this corner if I know that the capacity there is only good enough for 6? Or can I have them basically come one after the other to transport the goods into these production cell? Or should I split them over 2 different corridors that I don't have a bottleneck at a certain location? In the other way, this is also something where we have the task planning that is happening in the enterprise domain. And if we know from the network, well, there will be 4 new devices coming and they will be moving into this corner at that site, that is something that could be also used in the network for preparing for an upcoming traffic load. And with this, I come to a summary of saying, so if we look into this this layered architecture, the different paths that we have heard during the day, they are basically impacting the architecture in these different orange boxes that I have shown here. They are listed here on the left, but I have described that in the slides before. So since I'm almost out of time, I use some time to go this. So what does this mean in the practical realizations? And let's start with a local private network. So this is a figure that you have seen already in 2 presentations before. We assume a shop floor where we have then the top right, the server room where the edge cloud is hosted, where a lot of the, let's say, the compute for the environment is hosted. We have in the dark blue now a wired TSN backbone network that connects basically all the fixed assets in the factory. Then we have a couple of other access assets, which are, for example, the workers wearing the exoskeletons or having their XR classes, or it can be mobile robots, which are moving around and they are wirelessly connected. And then we connect these wireless devices into the backbone via the 6G network. When we take the approach on how the integration of 5G, 6G is used, if we extend this into 6G, it means that we have up here on the top, we have our cloud layer where, let's say, a lot of the functions are actually hosted. Then we have the assets which are connected in this middle gray TSN via the TSN backbone into this infrastructure. And the wireless devices are then via these virtual bridges or .NET nodes connected into this infrastructure as well here with the blue lines. If we think of a network, this is basically the way on how 5G TSN has been standardized for the 5G network. And now if we assume private networks of the future, I mean, they are being deployed right now as 5G networks. And when we come now with new capabilities with 6G, how would this look like? So we have our 5G network here that is now integrated into, let's say here, a factory environment. So with support for TSN.NET. And now if we add 6G, how does this work? So we assume that we will have a new, here in purple, radio access network for 6G that is added to this deployment. We see that that there will be, and we have heard this in the keynote at the beginning, that most likely in the core network there will be an evolution of the existing core network for integrating the new capabilities that are needed for supporting 6G devices and the 6G radio access network, for example, for sensing. But otherwise, we extend the capabilities that are already there for the 4G network. And then in order to make sure that, I mean, often in these local deployments, there's only a limited set of spectrum bands that are being used there. There we can use this multi-route spectrum sharing of the local spectrum that we can very dynamically basically use the spectrum for either the 6G or the 5G devices as needed. We had the other use case that was introduced by Oliver on the smart farming. There we are more in a wider area in which the operation works. And it's more likely that we will have a public network, which is the baseline for this connectivity. And in this case, we want to basically create a virtual dedicated network that is a private network slice, you can say, on a public network, which allows to have, we have our local assets then here in the smart farming area. These are the harvesters, the drones which identify the animals, for example, on the field. And we have a backbone where the applications for analysis and task planning are, which could be a private cloud or it could be hosted in a public cloud. And we want to connect now our assets locally into this domain by using part of this dedicated network slice. And this is something that for which we need configurability, and there's some work ongoing. For example, the Open Gateway Alliance, where APIs are defined for how you can put a request onto a network for example, defining a dedicated network as a service. And with that, I think I'm out of time and close here.
Great. Thank you very much, Joachim. Unfortunately, right now we don't have time for questions, but we can continue the discussion during the coffee break, and we need to conclude this part of the day. So I would like to say a big thanks for everyone who joined on site and online. We should say goodbye to the online participants, and here we could start a more interactive part of the day with a couple of demos. So please explore the demos on the area of security, network emulation, simulation framework, 5G TSN integration, and so on. And we can continue with a nice discussion with Cafe. So thank you, and let's continue. Great.
Thank you.